motivations for reactions. There we go. Okay, so we have enthalpy, which is heat energy, which would go into a system or out of a system. We have a special name for enthalpy when heat goes out of a system. What is it called?
Exothermic.
Exothermic. And we have a special name when heat energy goes into a system. What is that called?
Endothermic.
Endothermic. And then we have this crazy word that basically just means thermodynamically favored, and that is spontaneous. So our two drivers of whether the universe wants a reaction to happen or not are heat energy and entropy. So, does the universe want a reaction to become more entropic, more chaotic, or less? More. So, a positive delta S, an increase in entropy, is spontaneous. And a negative delta S is a decrease in entropy that is not spontaneous. And then, does the universe want heat to be released out of a system or into a system? Out. So, a negative enthalpy, in other words, the system is releasing heat, is thermodynamically favored, and a positive entropy, where it is becoming more chaotic, is favored. So we have two terms that we're going to put together to come up with a single value that says, does this system require energy, or does this system produce energy? Hopefully your phone is over there, and in that phone there's a little battery, and in that battery is a little chemical reaction, and the chemical reaction is releasing useful energy. So the useful energy, we're going to give the letter G, named after this guy named James or Willard Gibbs. I can't remember his first name is James. Anyway, his last name is Gibbs. So we have a G, and the G takes into account the enthalpy and the entropy change. Takes into account both. So I think it's James. Anyway, free energy is delta G, also called Gibbs free energy, because there's J. Willard Gibbs. And it basically says if you have a spontaneous or thermodynamically favored enthalpy, and you have a thermodynamically favored entropy, your system will release useful work that we, the surroundings, can use. On the other hand, if you have a thermodynamically unfavored enthalpy and a thermodynamically unfavored entropy, then you and I are going to have to produce energy, sending it into the system to make it go. So right now, the batteries in those phones are releasing energy to the little computers that run them. And then once they get to a certain point and aren't releasing useful energy, the battery is dead, and we recharge it by sending energy back in. So, what do you think the sign would be of a thermodynamically favored free energy? Remember, thinking about the system. If a thermodynamically favored system releases useful energy, what would the sign of a thermodynamically favored free energy look like?
Negative.
Negative. So, a negative delta A or negative delta G is thermodynamically favored. And what's the sign of a thermodynamically favored enthalpy?
Negative delta H.
Negative. And what is the sign of a thermodynamically favored entropy?
Positive.
Positive. Okay. So to make sure that a thermodynamically favored negative value is combined with a thermodynamically favored positive value will always return a negative value, you put a negative sign right here.
Wait, thermodynamically favored.
So if you had a negative minus a positive will always be a negative, right?
Yeah.
So that's why we need a negative, because a negative plus a positive might not be negative. But a negative minus a positive will always be negative. And there's one more term that we need to add here. And that is the thing that controls the value of entropy. What did I say controls the value of entropy yesterday? Determines how fast particles move. Not heat, but temperature. Temperature. So temperature controls how fast or how large the entropy term is. So this is Gibbs' equation. Delta G equals delta H minus T delta S. The free energy available to this, from up to us from the system, minus the enthalpy, equals the enthalpy minus the entropy term. And again, the entropy term is tied to temperature. Temperature magnifies the entropy term. Determines how big it is because it determines how much the particles are moving. Make sense so far?
Yeah, one second.
All right. So, if your enthalpy is thermodynamically favored, and your entropy is thermodynamically favored, your Gibbs free energy will be thermodynamically favored. Well, need a red pen. If your enthalpy is positive, that is thermodynamically unfavored, minus, equal. You guys realize temperature is always positive, right?
Yeah.
Temperature cannot change the sign of delta S, so we make it bigger or smaller. Can't change its sign. And what is the sign of a thermodynamically unfavored entropy? Negative.
Oh.
So, a positive minus a negative will always be what sign? Positive. Thermodynamically unfavored. Thermodynamically. I realize this is boring, but I have to say boring things. I'm a teacher and you're the student. I won't talk long though, I promise. Now, what happens if you have a thermodynamically favored enthalpy, but a thermodynamically unfavored entropy?
It could be either.
It could be either, but there's one value that determines whether this one is thermodynamically favored or thermodynamically favored or thermodynamically unfavored.
Would that be the temperature?
It would be thermodynamically favored and thermodynamically unfavored based on the temperature. Because temperature determines the magnitude of the entropy term. If temperature is really big, in this case, the system's going to be thermodynamically unfavored because the entropy term will be bigger. However, if temperature is very small, this system's going to be thermodynamically favored because the entropy term is very, very small. In the battle, if entropy and entropy are both thermodynamically favored, the system's always going to be thermodynamically favored. If enthalpy and entropy are thermodynamically unfavored, the system's always going to be thermodynamically unfavored. But if they're in conflict, temperature determines how big the entropy term is. Capiche? If you're comfortable with that, give me a thumbs up. If you have any questions at all, wave your hand around. Moving on. All right. So this is what we were talking about. This is a fun little chart you see all over the internet. If delta H, thermodynamically unfavored, thermodynamically unfavored, it's going to be non-spontaneous no matter what. Thermodynamically favored, it's going to be spontaneous no matter what. But if they are in conflict, temperature is going to determine whether the reaction is going to be spontaneous, because temperature determines the magnitude of the entropy term. Yeah. And then one thing that we're going to spend seriously a week talking about is equilibrium. If delta G is 0, that means the system is neither thermodynamically favored or thermodynamically unfavored. It is in perfect balance. We'll talk about perfect balance next week. All right. Questions? Moving on. All right, so there's that and that. I think we just bang this out. There's one super important thing about delta S. I mentioned delta S yesterday. It has the units of joules per mole Kelvin. So the delta S has the units of joules per mole Kelvin. Temperature has the units of Kelvin, but delta H has the units of kilojoules per mole, and delta G has units of kilojoules per mole. What that means is, and this is super important, is everyone paying attention? When you use your entropy term in Gibbs equation, you need to convert your joules to kilojoules. Yep, divide by 1,000. Because if your unit is getting larger, your number is getting smaller. So your unit is getting larger by 1,000, your number has to get smaller by 1,000. Comprende? Moving on. I think we're just about done. We have like one more slide. Yep, here we go. Okay, if enthalpy is non-spontaneous, but entropy is spontaneous, what determines whether the reaction is spontaneous? Temperature. So, if a reaction has a delta H of 340 kilojoules, oh, by the way, the calculators are up there. If a reaction has a delta H of 340 kilojoules per mole and a delta S of 3240 joules per mole Kelvin, is the reaction spontaneous at 470 Kelvin? So, do the work. Once you have an answer, show it to your neighbor and see if your neighbor agrees.
Mr. Myers,
Yes,
is delta G in kilojoules per mole?
it is.
Okay.
That's also the case on your thermodynamic data table. It'll show entropy as joules per mole Kelvin, enthalpy and Gibbs will always be in kilojoules. All right, so we have a thermodynamically unfavored positive 340 kilojoules per mole. Temperature is always positive no matter what. Minus 470 Kelvin?
Yeah.
470 Kelvin. And then the delta S is a thermodynamically favored 3.240 kilojoules per mole Kelvin. Is that what you guys got?
Yeah.
Is that your work look at that? So what is the final value that delta G comes back with?
Negative
5-minute warning.
1,500.
Ignore that.
2.
Alexa, stop. It worked. Okay. What, negative what?
1,522.
1,522 kilojoules per mole?
Yeah.
That seems way too big.
Yeah. 1,100.
That sounds better. So watch out for your signs here. Make sure you're putting this in parentheses if your calculator doesn't do it for you. Negative 1,100?
80.
1,100? What that you said 1,082?
1182.
1182. Okay. 1182 negative, right?
Yes.
Kilojoules. So that system is thermodynamically favored. It is spontaneous.
340 minus the
Yeah.
Oh, it does. Negative 115.
Probably just
I got negative 1164.
Well, clearly, all the calculators are giving us different answers, so it's clear the calculator's fault. So let's move forward. If a reaction has a delta H of negative 110, that is thermodynamically favored, and a delta S of negative 1524, which is thermodynamically unfavored, what temperatures make the reaction spontaneous?
So do we have to like equal and a greater or something?
Yep. So you're going to solve for T, and you're going to get a number. And you're going to say all temperatures above this number or all temperatures below this number. Work it out.
Ooh, what? Alright.
So are we gonna make delta G equal to like -1 to 0?
Zero.
Okay.
Because you're going to you're comparing the two, so you're going to make them equal to 0. Make delta G equal to 0. Which makes sense. It is the point at which a thermodynamically favored system becomes unfavored, or an unfavored becomes favored. Ultimately, we're going to look at delta H and delta S, and we're going to say all temperatures above this, or all temperatures below this.
So do we
Okay, what is the cutoff point? What temperature is the cutoff between the two? The temperature at which a non-spontaneous becomes spontaneous, or spontaneous becomes non-spontaneous.
0 like -0.
531 Kelvin?
Yes.
So that's 810 divided by 1.524?
Yes.
Okay. So you said 510 Kelvin?
31.
31 Kelvin. Okay. 531 Kelvin. Now we got to know what should go here. Is it all temperatures above 531 or all temperatures below 531? Look at our numbers.
Above.
We have an enthalpy
Below.
that is thermodynamically favored and an entropy that is thermodynamically unfavored. So do we want the entropy term to get larger or smaller? Smaller. So it's all temperatures below 531. Because again, temperature determines the magnitude of the entropy term. If our entropy is thermodynamically favored, we want high temps. If our entropy is thermodynamically unfavored, we want low temps. Is that clear?
Yeah.
There was a bunch of those kind of questions on the test. Two, anyway. Still, it's going to feel like a bunch. And I think this is it. Yeah, all right. Okay. A reaction was found to be spontaneous at temperatures above 1200 Kelvin and non-spontaneous below 1200 Kelvin. If its enthalpy is 852 kilojoules per mole, what is the entropy? Work this one out. If you have an answer, show your neighbor and see if you can come to a consensus.
So is delta G still 0?
0 is that number that is between the positive and the negative values.
That is true.
Wait, doesn't that mean that the entropy could be like a bunch of different numbers too?
No.
Oh, shoot.
It's telling you that it's the cutoff is exactly 1200.
Oh, okay, okay. Maybe it's 0.7.
I got 1,400. I don't know what I did. It's probably wrong. But
What did I do?
I mean, it probably Good one.
What did you?
I did 1200 by 52. And like 1.4 or something. I did that times. Oh, so
I know.
When I was growing up, we didn't have colors. We had chalk. White.
I hate chalk.
Could they buy like different colored chalk back?
I suppose they could have, but they never did. Did they have colored chalk back in the 80s?
When we answer for the entropy, do we do it in the kilojoules or the joules per mole Kelvin?
Excellent question. Since it is an entropy value, you're going to answer it in joules per mole Kelvin.
Okay.
Okay, so 700. Is that what you got?
What would you get?
Negative.
That was positive. It's wait.
The country you got 710.
High temperatures of are spontaneous, so that means your entropy term is going to be spontaneous, so it's going to be positive. So you got a value of 0.7 something something to begin with. 710?
Yeah.
And that's going to be in kilojoules per mole Kelvin. And then you're going to turn that into 710 joules per mole Kelvin. How are you feeling about this? Pretty good. Okay. Well, you don't have a lot of time to work on your worksheet. But that's okay because you can continue to work on it next Monday during our lab or after our lab. So you can go ahead and work on your own. This is kind of fun. I just put this here because I thought it was fun to make. Because the universe likes fireworks. All right. Any questions before you work on your own for the last 15 minutes of class? All right, off you go.
Just about tired of that.
That's a question.
That's
You
a
can ask a
question,
question.
buddy.
Yes, you may.